According to plate tectonics, the present-day Earth consists of 12 major plates, which move in various directions. This plate motion causes them to collide, pull apart, or scrape against each other. As a result of plate tectonics, present-day scientists recognize a so-called ring of fire, the chain of active volcanoes and earthquakes located along the plate boundaries. Plate tectonics recognizes three types of relative plate motion. Mantle convection and convection flows. The temperature inside of the Earth's outer and inner core is about 5,000 to 6,000 degrees Celsius. Heat from within the Earth results in convection flows below the lithosphere. These flows put the plates into motion. The ductile asthenosphere zone is weak, easily deformed, and acts as a lubricant for the tectonic plates to slide over. The sketch above shows convection cells in the mantle of the Earth. This analogy is commonly seen in boiling water or soup. However, such a comparison doesn't take into account the huge differences in the size and flow rates of these cells. This schematic combines the asthenosphere-lithosphere interactions and positions of the convergent, divergent, and transform plate boundaries. Focus your attention to the formation of the deep trench formed at the ocean-continent convergent boundary, as well as the ocean-island arc boundaries. Processes that occur at ocean-continent convergent boundaries. At the continental margins, heavy and dense oceanic lithosphere subducted beneath the continental plate. Subduction is a geological process that takes place when one plate moves under another and is forced to sink due to gravity into the mantle. Partly molten materials cause volcanic eruptions, forming chains of volcanoes. Processes at divergent plate boundaries. At the oceanic floors are chains of mountains. Oceanic plates move apart at mid-ocean ridges, causing seafloor spreading. During oceanic floor spreading, a new oceanic crust forms. This animation shows how new portions of oceanic crust are created during seafloor spreading. Seafloor spreading over millions of years continues to push the continents apart. This map shows the structure of the Atlantic Basin ocean floor between North American, South American, and Eurasian African plates. You may be familiar with volcanic eruptions in the Hawaiian Islands. How are they formed? The Hawaiian Islands are formed by hotspots, not by plate boundary movement. The Hawaiian Islands have no continental crust. They are formed by the mantle plume, magma rising from the mantle and penetrating the oceanic lithosphere. This process of island formation is called a hotspot. Continent-continent collision is a phenomenon of the plate tectonics of Earth that occurs at convergent boundaries. Continental collision is a variation on the subduction processes, whereby the subduction zone is destroyed, mountains formed, and two continents sutured together. The India and Asian plate collision. It started as subduction of the seafloor under Asian continental margin, continent convergent boundary. India started to move towards the Asian continent 70 million years ago and collided with the continent 10 million years ago. This collision led to the formation of the Himalayan mountains. The collision of continents reshapes relief of our planet. The India-Asia collision led to the formation of the Himalayan mountains, including Everest, the highest mountain peak on Earth, at about 8,848 meters high. The three groups of rocks are igneous, sedimentary, and metamorphic. Igneous rocks crystallize from a melt, which originates from the Earth's mantle and crust. Examples of intrusive igneous rocks include granite, gabbro, and peridotite. Examples of volcanic or extrusive igneous rocks include rhyolite, basalt, and comatite. Sedimentary rocks, deposited on the Earth's surface and at the bottom of lakes, seas, oceans. Shale, limestone, sandstone, and clay. Metamorphic rocks, former sedimentary or magmatic rocks recrystallized and deformed at depths approximately 5 to 30 kilometers, temperature 5 to 900 degrees Celsius, and pressure 1 to 5 kilobars, formed in the Earth's crust and mantle. These images represent major groups of intrusive and volcanic rocks. The images of major sedimentary rock types are presented here. Metamorphic rocks are a very diverse group because they're protolith, a primary rock before the metamorphic recrystallization, may be presented by all types of igneous and sedimentary rocks. Here we demonstrate a few examples of them. Garnet mica schist, gneiss and eclogite. The rock cycle is a simplified geological model which shows that, number 1, solid rocks in the earth mantle are partially melted. 2 and 3, igneous rocks, which are generated by magma from mantle and crust, can change into sediments through weathering and erosion. Number 5, loose sediments through the process of lithification are converted to sedimentary rocks. Number 6, sedimentary rocks, in their turn, can change into metamorphic rock when they are subjected to recrystallization at high temperatures and high pressures. Metamorphic rock can change into igneous or sedimentary rock, and therefore the rock cycle continues to change our planet throughout geological time. Rocks consist of minerals. As you can see, they look different. Minerals, in turn, consist of elements. Let's see their connections. If you analyze the periodic table of chemical elements, you will see that currently there are a total of 118 different elements. About 90 of them are found in rocks and minerals, while the remaining 28 elements have been synthesized in laboratories and nuclear accelerators. There are approximately 4,200 minerals in the Earth. 1 or 2 minerals are discovered each year. The minerals are made up from the 90 elements that occur in different minerals in different combinations and in different proportions. What are minerals? Minerals are naturally occurring, found in nature, solid crystalline substances, usually inorganic, not a product of living organisms, with a specific chemical formula. It means a unique chemical composition and an ordered atomic arrangement, or atomic structure. Minerals exhibit diverse physical properties that are used for their identification. To identify minerals in the field, geologists use the following properties: color, hardness, and cleavage. Color. This is one of the most obvious properties of minerals, though color is not always a reliable means for mineral identification. Hardness. Minerals' hardness is compared on the Mohs hardness scale, a 10-point scale running from the softest talc to the hardest diamond. Cleavage. This is the tendency of a mineral to split along certain planar surfaces that correspond to the weakest atomic bonding. The image at the right shows halite crystals, which exhibit perfect cleavage in 3 directions. The chemical composition of minerals are represented by a general chemical formula. For example, the mineral quartz, the major component of Earth's continental crust, consists of silicon and oxygen, and its chemical formula is SiO2. The mineral olivine, the major component of the Earth's mantle, consists of magnesium, iron, silicon, and oxygen, and its general chemical formula is 2 atoms of magnesium or iron, 1 atom silicon, and 4 atoms oxygen. The composition of minerals are measured by special X-ray spectrometers and electron microprobe instruments. They will be shown in the virtual laboratory section. Mineral structure is also called crystalline lattice. Crystalline lattice consists of ordered arrangements of atoms. To understand this, let's consider atoms as being spheres of different radii and imagine a silica tetrahedron. The tetrahedron consists of one low radii silicon atom surrounded by 4 large radii oxygen atoms. Now prepare for a quiz.